Ladies and gentlemen, we are live. Thank you for following along. We're going to be coding GPT-2 with MLX today. So that's right. I am GPU poor and I have an Apple computer. So that means I'm GPU poor, but Apple rich. And I thought I'd like to learn how to code and figure out GPT-2. Andre Kaparthi has blessed the entire world with 10 years of his knowledge plus on YouTube for teaching us how to make GPT-2, all the way down from like getting the data and training it and so forth. And I've been lucky enough to be online and have like my little setup here. So we got multiple cameras going on today. We're also going to be doing some screen sharing here. And this was actually inspired by my friend Ronald Monag, as you can see above. So it's basically my birthday wish. And I've been wanting to train and figure and learn how all this stuff works in machine learning. And sometimes I feel like I've missed the boat, and I actually haven't. You know, it turns out that like you can just learn anything you want if you apply yourself. So I'm making an effort to show up every single day. It doesn't matter what. The day is almost ended. It's almost like it's 9 o'clock here, 9:42. I said I have to do a stream today because this is day 3. People are waiting for me. They're looking forward to this, and this is a forcing function here. So we're going to show up every day, work on this, figure out how this works. Going to work at our own pace, and I'm going to kind of chunk things down so they're just like, it's not really a speed run. The whole point of this is to understand how this is built and build it ourselves. And since I don't have an NVIDIA GPU, I just have a Mac. We're going to build it with MLX. So we're going to be following along with this guide from this guy named Prabnav, who's posted this actually on Medium and has also posted it on GitHub. And what's nice about it is I actually have it together here on my blog. So, Kidis Adunga. Go Ray. Thank you so much. Yeah, if you got the comments, definitely drop them in. I'll be definitely featuring y'all guys. Definitely appreciate the love and the people who've been hanging out here to support us, because this is happening right now. This is really, really cool. So without further ado, let me move my head over here a little bit so we can kind of see what's going on. All right, so GPT from scratch with MLX. And as you can see here, I'll have all the episodes listed so that you can go back reference. And this is just at rayfernando.ai. So if you type that in, you'll be basically taken here. And at the very top of this whole thing, you're going to have my little GPT from scratch. So in here, I'm basically going to have the episode list. And if you wanted to see like the entire, you can just click one of these tags and it's going to take you to all the different posts here. Just do a hard refresh and it should hit my server. But yeah, so that's there. So this is GPT from scratch. And then as I'm going through and actually updating it, this is all based off Notion. So I'll just update my Notion notebook and you'll see all the changes in here instantaneously, just for you. So if you have any questions, feel free to ask. This is our session together. We're going to basically do some late night coding session here, and we're just going to vibe. I got the music going on. I got the multiple cameras over here. You know what I mean? Just doing it real Godzilla big. That's right. I should be looking over here, looking at you. That's right. All right, so let's get this going. I just love this whole live stream stuff and just kind of vibing with everyone. So I'm glad you're able to also appreciate my vibes too. So let's go ahead and get cracking on this. So let me just kind of get a little bit organized here. And if you haven't had a chance to, definitely retweet. So if you're watching live now on X or on YouTube, I would say like repost / retweet. And what ends up happening is that anyone else who's watching or who's online will be able to see this. So that actually kind of helps the algorithm with all the goodness here. So let's take a look. So last time what we were doing here, we took a look at the previous days. So we just kind of go back to this entire guide. We started out with preparing the data and getting our IDE set up. So that's what we have set up right here with Anaconda. And then we went through like creating the vocabulary, and that just means we got the whole Shakespeare, million lines of text and stuff like that, and have put that in, and then created this encoder to basically encode the text and then decode the stuff back out, and we get these little numbers. And then we also learned about the training data and the sets. So setting up our training data for the inputs, basically these chains of numbers, and then the labels of like what's going to be predicted next. And if you remember from the last time, if we get these 3 here, the next sequence would be the one that's pointed down below, which is 57. So that's just kind of a refresher there from yesterday. And then we went through creating the training and validation data sets as well by setting up those X and Y values. And then we set up the batch sizes. And so the batch sizes were similar to what I was talking about, like when you're cooking on a stove. If you have 4 burners, you don't want to just put everything in one and just, it's just a waste because you have 3 other ones you could be using. So here we can take advantage of this ecosystem just by, using the other burners by doing 4 batches. So that's kind of the parallel here. And so these computers can do these things. So we set up these batches, and that's kind of what we're doing. This is the inputs, and then these are the labels. It can look confusing, but it just kind of, you have to kind of maybe visualize it. And I would highly suggest if you have any problems, just pop that into like another language model like Claude Sonnet and have it explained to you as well. So today it's going to be looking at coding GPT. So let's look at the GPT architecture. And so this is this stream is kind of meant to be vibes right now. I got some music playing in the background so that we can just chill. Late night coding in the dock. All right, shout outs. So let's take a look at the GPT-2 architecture to get an overview of what we're doing. And also let me allow accessory to connect. Sure. I guess my camera is freaking out. Something happened. Oh, sorry. I'm just trying to get my stream together. Okay, cool. All right, kids, let's do this. So according to this, we have the architecture overview here and image by author. So we have the NX transformer block. And let's see, how does it start here? It says positional embedding, input embedding. So this is, I guess, our input for the embedding. And then this is the position. So it goes in and it kind of goes up into this. And it looks like it takes a split. So it goes into the first, what it calls like the layer norm. And then it comes back out to the end. So like whatever we put in also gets added to the end of this. And so when it goes to that first layer normalization, I guess it's like a mathematical equation or something like that. And by the way, I'm just like kind of winging this by hand and just trying to digest what's going on because I've never done this before and we're learning together. So that's what it is. Multi-head attention self is the next step there. And it looks like then we do a linear plus dropout. So it's probably some mathematical application here as like these goes through these steps. And it looks like you feed in whatever this positional embedding and the input embedding that came in to this. That's basically the transformer block. And then it goes in again to the next layer normalization. It goes to the MLP, whatever that is. Then it does another dropout. Instead of a linear dropout, it just does a regular dropout. And then it takes this that we added back in and all of this mathematical gooiness and then applies that back again and then like poops it back out of the transformer block, literally boom. And then we go through again, another layer norm and then the linear. And then we go through the softmax and next token possibilities. Okay. Are you picking up what I'm putting down? It sounds heavy, right? Okay. So I guess that's kind of what it is. Let me make sure my other camera's set up because I had the 2 cam set up and I'm just going to plug that one back in just in case. Yeah. So dealing with multiple cameras can be a little interesting here. So just making sure everything's Gucci. Okay. Yeah, we are. Cool. All right. So that's a little bit of this architecture. Don't worry if this looks confusing. We'll implement it in a step-by-step from the bottom to the top. Let's start by implementing the input embeddings. Okay. So I guess for me, what I wanted to do here was mostly understand, like before I get coding, before I kind of get into the things, I like to visually, mentally map what's going on and like ask questions. And by asking these questions, they kind of stick in my head. So as I encounter them in the future, they'll start to get answered. It's just the way that I learn, but it kind of works that way. And sometimes like the best equivalent to this is maybe like if you get a book, kind of looking at the index, like actually flipping through the book and looking through the chapters so you can kind of get a heads up of what's going on. And so that can give you like a mental model of like how the information is laid out so that you know kind of what to expect. You're like, oh, I heard of multi-head attention. That's right. Yeah, that was mentioned. Now this is coming in. Okay. And so the goal of this is to kind of put your brain out there and kind of spread it out on the table. And then you'll start to make these connections in different ways. So just the way I approach it. And then you get the beats. Let's go. Okay. Trying to make learning fun, right? This is really thick stuff, by the way. I don't even know how these people like figured out, they're just like, yeah, if we just do all this math, we're just going to like create this thing that's going to just change the whole world. Okay. Just low key, by accident, I guess. I don't know. It was input embeddings. So input embeddings, the purpose of the input embedding layer is to map token IDs to vectors. Map token IDs to vectors. Each token will be mapped to a vector, which will be its representation as it's forwarded through the model. Each token. Okay, so the purpose of the input embedding layer, which is this guy, is to map token IDs to vectors. Okay. The whole thing, this is just to map the IDs to the vectors, which is, I don't think they mentioned a vector in here. Okay. Each token will be mapped to a vector, which will be its representation as forwarded through the model. So I guess when it's put in, it's mapped to a vector, and that's how it's represented when it's pushed through the model. Okay. I believe you. The vectors for each token will accumulate and exchange information as they pass through the model and eventually be used to predict the next token. These vectors are called embeddings. Okay. So these are the embeddings. Embedding dimension, vocab size. Okay. The simplest way to map token IDs to vectors is through a lookup table. The simplest way to map token IDs to vectors is through a lookup table. Okay, so if you have a token and you have the ID, and like the way to map them is through a lookup table, basically these little matrix things. So we create a matrix size of vocab size, comma, and embedding. So the vocab size is where each row is in the embedding vector for the corresponding token. The matrix is known as embedding weights. Okay, yo, I think this is getting too like thick right now. So let me just pop in some Claude Sonnet and let's get popping on this, because why not? I mean, that's what we have the GPTs for. So explain this to a fifth grader. I'm like, what is a vector and its relationship to a token? Okay. Boom. Let's see what it does. Okay. Let's imagine we're talking about a special language game for fifth graders. Oh, come on. Oh, I guess this is the thing when it streams, it kind of does this little skippity bounce. Okay. Here's how we can think about vectors and tokens. Tokens. Think of tokens like words in a secret language. Each word or piece of a word is given a special number. For example, word cat might appear as number 42 and the dog might be number 73. Yeah, I think that's kind of what we did when we were doing those embedding things. Okay, so that's the token thing. Vectors. Now imagine each of these special code numbers, tokens, has a magic backpack. Yo, is this why Sam Altman has that backpack? He has the blue bag because he's basically like, he's got the vectors. I don't know. It's kind of an inside joke, but yeah, let's continue on here. Let me change the camera angle too, so y'all can see the. Okay, so right here. So now imagine each of these special code numbers, tokens, has a magic backpack. This backpack doesn't contain regular things like books or pencils. Instead, it's filled with a list of special numbers. This list of numbers is what we call a vector. So literally the tokens have like this magic backpack, and the magic backpack doesn't have like what you would expect, but it has a list of special numbers. And that's what they call a vector. So it's like, yo, dog, I heard you like numbers. So your numbers got numbers so that we can carry the numbers through these numbers. Okay, I got you. That's a little bit too meta for me, but yeah, okay. How they work together. When we use our secret code language, we don't just use these code numbers, tokens. We use the whole magic backpack, which is a vector, that goes with each code number. So this backpack helps our computer friend understand the meaning of and context of each word better. When we use our secret code language, so there's like a secret code language apparently. Okay, tell me more. We don't just use the code numbers, which are the tokens. So I guess they don't just pass around the tokens. We use the magic backpack, which is the vector. So the vector is like these list of numbers that goes with each code number. I guess the backpack in this case is kind of the relationship that is specific to that token. So I guess if you have the word cat, you're going to have this long list of these like numbers in this backpack. And then that's basically all the relationships that are related to cat in every single way. So like cat that is seen by whatever the space is in the world. So if you see cat, you see cat with a hat because there's a book called Cat in a Hat. And then you'll see cat with like dogs, and you'll see, so like I guess these numbers that are in the backpack are sort of representations of what cat, this little word, token of cat can mean. Okay, this is making way more sense now. Okay, that's what we're doing here. Okay, I think it took me a little while to figure out, but that's kind of what we're doing here. So the big picture is, imagine you're writing a story using the secret code. As you write each word, token, you're actually handing over a series of magic backpacks, vectors, to your computer friend. So your friend looks at all these backpacks together to try to understand your story, and guess what word may come next? Oh, okay. So like imagine this is sort of coming together now. So like imagine like we're basically having this, like trying to predict what the next word is, but all you have is these backpacks, right? So then you're like literally taking apart every backpack. So as you get one backpack, you'll kind of figure out what the next thing is. You're like, okay, this backpack is related to a cat. And then like of the next things that could happen, it could be cat in the hat, cat in the like bag, cat next to a dog, cat, whatever. And then you get the next backpack and then you open that up and it's like, bzz, okay, this is cat in a, and then like, whoa, okay, so that is this one. And then like, so those vectors are basically kind of what gets thrown in as the backpack. And then the tokens are like the word. And that's kind of like what we're, I guess, unwrapping here. Okay, this is the token and vector relationship. This is making more sense. Every time I think of vectors, everyone draws that little like line graph thing and it goes into like dimensions. And I'm like, okay, I guess let me ask it about dimensions because I don't see dimensions in here. So what are dimensions in this context? Right? I mean, let's go. Let's see. Great question. Let's explain dimensions in the context, still keeping like the backpack. Okay. So while that's generating its thing, we're going to figure out what that's going to be next. And so basically looking back at this Claude. So the big picture, imagine you're writing a story using secret code where each token, you're actually handing over a series of magic backpacks, which are vectors, to your computer friend. And your friend looks at all these backpacks together to understand your story and guess what word may come next. So in simple terms, a token is like a code number for a word or a part of a word, like we were saying, like cat, right? And so a vector is like a magic backpack full of numbers that it helps explain what the word means. And then together, they help computers understand and work with language in a special way. Okay. And then that's, okay, I think this makes more sense. Like, I feel like this is kind of like my, language models and machine learning for yeah, I have an engineering, like non-traditional background. I dropped out of school and I just like learn on my own. And this is just how I learn. I don't have a traditional background in like education, formal education or computer science or anything like that. So if I did, I think it would make things worse because I just would be using computer science terms to explain things like the way they're explaining it back to me. But that's just not the way I learn. So the way I learn is just by trying to like use these different concepts that I know in the world and then bring them down to simpler terms. And I think by you hanging out with me and me talking to you about it, I can kind of learn and maybe explain it. And maybe if you can pick it up, what I'm putting down, then like, I think that's kind of cool. So I hope it's helpful. This is just me trying to learn with y'all. So yeah, give a thumbs up. If you're watching along, thank you for joining into the late night stream. We're basically trying to code GPT-2 from scratch, but we're also kind of going through this a little bit slower and just trying to really understand, what is a token? What is really a vector? In the code, we can sort of look at it, but also like, what does that mean in these relationships? Because these are something that I've kept seeing over and over again, and it's going to keep coming up. And I feel like the more grounded we understand, like this should be simple to understand. Like somebody should be simply able to explain it to you. And like the backpack thing is a really great sticky explanation of how to do this. So yeah, that's kind of where we're at, fam. So, all right. So, okay. So the next thing we asked about was like dimensions. And people usually like to draw like the 2D graph and the 3D graph, and then like these dimensions kind of go off the charts, right? So this is what we're going to find out. So dimensions are like different types of information we put into our magic backpack, like a vector for each word token. So let's break it down. Imagine your magic backpack. Remember how we said each word has a magic backpack full of numbers? Well, the number of pockets in this backpack is what we call dimensions. So the backpack has pockets, and that's a dimension. Let's go. Okay. So the pockets in the backpack, let's say each backpack has 100 pockets. Each pocket holds one piece of information about the word. This means our vector has 100 dimensions. Okay. So what goes in these pockets? Each pocket might hold information about different aspects of the word. For example, one pocket might have a number about how positive or negative the word is. Another may have info of whether it's a noun, verb, or adjective. Yet another might tell us if it's related to animals, food, or weather. Let's go. So why do we need so many pockets? The more pockets and dimensions we have, the more detailed information we can store about each word. This helps our computer friend understand language better. All backpacks are the same size, so every word in our code language gets a backpack with the same number of pockets. This way, our computer friend can easily compare and work with all the words. So in this context, dimensions are like the number of pockets in our magic backpack. They represent how much and what kinds of information we are storing about each word to help our computers understand the language. This is fire. This is like finally mind-blowing. Okay, so vector, token, dimension. There's a token, there's a vector, there's a dimension. Are you getting it? So like the token is like the secret word, and then the word has a backpack, and the backpack is basically like the vector, right? And so that's kind of related to what the token is. And then the pockets inside are those dimensions, and each pocket is like a piece of information that kind of gives more meaning to what the backpack, and then even the greater like word could be, which is like the token. And so, wow. Okay. So now when someone says like, X dimensions or has 30 dimensions and so forth, that just describes like the vectors that you hand that in, and like gives more meaning to the tokens. And so that's, I guess, which to me, one of my thinking here, and maybe this could kind of, we'll probably learn a bit about this a little bit more, but it's like, I guess when you have more data in your data sets, when you give it to the model, less like filling each of those pockets and building those relationships each time, it builds the little token. So like when it makes, the tokenizer is the one that's going to, chunk down the words and then create these little vectors, which have these like, pockets inside them, which give more of the meaning to them. Oh my God, it finally makes sense. Kind of. We'll see. We're just got to get it started. So yeah. Okay, so let's move along here. So, all right. So we're at this phase now. So we're in input embedding. So the simplest way to map token IDs to vectors is through a lookup table, which is kind of what we're doing here. We create a matrix size where each row is embedding the vector for the corresponding token, and the matrix shown is embedding weights. Okay. So the diagram shows an example of embedding layer size 65, which is down here, and then 6. This means that the with vocab size is 65, and then the n embedding, which is the number embedding, was 6. So 1, 2. Okay. So this means that there are 65 tokens in the vocabulary. Each one will be represented by a length of 6 embedding vector. So the 6 is the length of the embedding vector. Remember those little the backpacks things? It's like the backpack size is like 6. The inputted sequence will be used to index the embedding weights to get the vector corresponding for each token. Remember the mini batches we input into the model. Originally, the mini batch size, context length. After passing through the embedding layer, its size, batch size, CTN, LAMB, instead of each token will be single integer. Each token is now a vector length and embedding. So let's define the embedding layer in code now. So let's go ahead and grab this code and put it in here. All right, let's go. Let me move my head to over here, and then we'll switch the cameras because why not? Yo. Cool. And so let's let me put me down here. Just kind of squeeze me down. Get the beats. For some reason, my beats are just not always going. All right, so we're doing this, fam. We're doing this. We're actually going to learn GPT from scratch, and it's a hairy one, kind of low key. Yeah, I'll put myself down here. All right, let me see. Just kind of fixing. Excuse my somewhat technical difficulties. Not really, but we're out here. Mini me. Okay. Let me move myself. Yeah. All right, that's better. And then move me down here. All right. Cool. That way I can watch the stream together with y'all. All right. So, and embedding. So you can add these hyperparams at the top of your file. Okay, that's what we're at. And then we take that NN module, self-init embedding. Okay. So we're just creating an embedding with a GPT. Great, gotcha. So we define a class to our organization, organize our implementation. We subclass NN module to take advantage of MLX's features. Okay. Then in the init function, we'll call superclass constructor and initialize our token embedding layer called WTE. WTE, mate. Okay. So let's get it. Positional embeddings. Next up in the positional embeddings, the purpose of the positional embeddings is to encode information about the position of each token in the sequence. So positional embedding. So I remember the embedding stuff, and then there's like the little positions that kind of move across. And then when we have the input, we map that to the label, which is down at the bottom above. Okay, so this can be added to our input embeddings, and we get a complete representation of each token that contains information about the token's position in the sequence. Okay, let's go ahead and grab this guy, copied. And so that's basically this token embed. So I think that's basically this. Yeah. Right? Yep. So the position embeddings work the same as the token embeddings, except instead of having a row for each token, we now have a row for each possible position index. This means our embedding weights will shape the context length and embeddings. Now we implement the call function into our GPT class. This function will contain the forward pass of the model. So the tensor shapes commented. So these are the tensor shapes here. I feel like I gotta watch the Kaparthi video to kind of see what he's talking about here, because it's a little bit over my head right now. Let's see. This is going to be tabbed in. Okay. So first, we break out the dimensions of our input into variables b and t, which is here. For easy handling, in the sequence modeling, context b and t are usually used as a shorthand for batch and time dimensions. In this case, the time dimension of our sequence is the context length. So, yeah, so the time, okay, that's the context length. And then, so the token embedding and the possible positional embedding are kind of here because they're initialized from WTE, which is right up here from the token embeddings. And then WPE, which is initialized from the positional embeddings, right? So we have that here. And then we basically take these two and then assign it to X. So this is the tensor shapes, right? I think so. That's just kind of what I'm guessing here. Now we calculate the token and position embeddings. Notice that the position embeddings, our input is MX arranged to T. This is right here. This will output an array of consecutive integers from 0 to T minus 1, which is exactly what we want because those are the positions we want to embed. It's exactly what we want because these are positions. Okay. After passing through the embedding layer, we will have a tensor of shape T and embed because embedding layer plucks out the n embed length vector for each of the T positions. Note that even though position embedding is not the same shape as token embedding, we can add the two because MLX will broadcast or replicate positional embedding across the batch dimensions to allow element-wise addition. Finally, we perform the addition to get the new representation of the tokens with positional information. So let's take this section with positional embeddings and then kind of do the same thing. Now, help explain this. All of the things. Let's go. Just curious. Like, this is how you use AI to help you. All right, ladies and gentlemen, let's see what's up. All right, let's break down into simpler terms. Continuing with our magic backpack analogy. I love this analogy, and I love that you can just keep passing it in and it just kind of knows what to do with it. So that's it is what it is. So positional embeddings. So imagine that in addition to our magic backpack for each word, we have a special sticker for each position in the sentence. So these stickers help our computer friend understand where each word is placed in the sentence. So that sticker is going to be like, yo, that's placed over there. Okay, this sticker's placed over there. So that's a positional embedding. Okay, so that'll tell you where the word should be placed. Okay, why do we need this? Sometimes the order of words matters a lot in understanding a sentence. For example, the cat chased the mouse means something different from the mouse chased the cat. Let's go. This is what I'm here for. How it works. Each position in the sentence, first word, second word, third word, etc., gets its own magic sticker. So this sticker has the same number of information pockets as our word backpacks. This sticker has the same number of information pockets. So the sticker now has pockets. Bro, this goes deep. This go Yo, these embeddings go deep. If you know what I'm saying? Like that is mad. Okay, so not only do your backpacks have pockets, but your stickers got pockets too. Sheesh. Oh man, I forgot to hit record for the transcript. It's okay. I just hit record now for my limitless. Do you hit the thumbs up if you're kind of understanding what's going on, and like just drop any comments, and I'll slide you right in, because I definitely appreciate y'all for tuning in, because this is getting really deep. But I'm trying to keep these to 25 to about 45 minutes, and we're at the 32-minute mark. So we're kind of towards the end of this section here, which is with GPT, and we have kind of started going through the code. And why I'm really kind of chunking this down is that this is kind of geared towards the busy person. Like, I'm a busy person. I'm trying to do, my normal thing as well as do other things as well. And you probably have a job and other things, and you're late night trying to learn. And you may have the same questions that I have, and you can kind of learn something from me, just kind of learning this together. So I definitely appreciate you kind of staying on. And as we go through this, it's pretty, it's not an easy topic to digest, but we're doing this here. So let's get back to the training here. So let's get this here. Okay. Let's go. So we went back to the positional embeddings. In addition to our magic backpack, we have a special sticker for each position in the sentence, right? Why do we need this? Sometimes order of words matter, because that's the chase the cat, backwards. So how it works, each position in the sentence, first word, second word, third word, gets its own magic sticker. This sticker has the same number of information pockets as our word backpacks. So that we stick this position sticker onto our word backpack. In the code, self WTE is like our collection of word backpacks. Okay. So if I go back, WTE, which was initialized here and which was described up here as a token embed, is the collection of our word backpacks. Okay, so then remember the tokens, those little word things? I think you're over here. Okay, cool. Those are the tokens, and then the tokens have backpacks, a whole set of backpacks. So the WTE is the collection there. Okay, so self.WTE is that shape. And then the WPEs are a collection of the positional stickers. So the stickers are the ones that then come in. So putting it all together, when we process a sentence, we get the magic backpack for each word. So when we process, we put a whole sentence in, we get the magic backpack for each word, which is the token embedding. And then we get the position sticker for each spot in the sentence. That's a positional embedding. And then add the information from the position sticker to each word in the backpack, which is the token embedding plus the position embedding, which is X. So the result now, now each word's backpack, with those little blue backpacks, contain both the information about the word itself and the information about where it is in the sentence. So back to here. So the little backpacks will say, exactly where the word belongs in the sentence. So that way, when you get something back, it'll say the cat chased the mouse, not the mouse chased the cat, because those, while they are together, they can be kind of also reversed. So like the sticker is the one that tells it, no, cat goes before mouse, vice versa. So that's cool. Okay, lots of other questions, but I'll keep this a little bit brief. So we're going to get towards the end. So this helps our computer friend understand not just what words are being used, but also how they're arranged. Right. So think of it like this. If you're in a race, it matters not just that you're in the race, but also what position you're in. These positional embeddings help give that position in the race information to each word in the sentence. Damn, this is so good. This is so good. This is really awesome. So this is super helpful for me to understand some of these words, but then also start applying them to other concepts so that I'm not really, lost too much in the technicals of the language, right? Because that's what it is here. So far we have the code here that has a tensor shape. We haven't actually executed the code because it's not going to do anything. It just sets up the class for it. I mean, if I hit run, it's just going to just say, yeah, the input labels and stuff that were back here that we printed out are printed out, but there's nothing in here that we're really doing. So, cool. So the next step is going to be self-attention. So we're at 36 minutes. So naive self-attention. So this is the input sequence, and these are the new representations. So 4 tokens and input embedding average over previous tokens. So this is the input sequence. So we just take the inputs and then it derives new representations. So that average over the previous tokens. But the self-attention doesn't involve writing a loop. So attention weights times input sequence equals new representations. Softmax for each row. And these steps, because it says self-attention, and then this one also says attention weights and new representations. If we go back to the architecture diagram, self-attention and new weights, new head self-attention. I think it's kind of like dealing either with here or somewhere up here. I'm not really sure. So maybe we'll find out more tomorrow, kids. Queries, values, just kind of scrolling down. Attention. Okay. Don't worry. Don't get too overwhelmed. Even though it could feel that way. Don't buy into that. This is not the space for that. It's the space to vibe and learn and be chill together. Stealthy Slacks. I appreciate you with the wave on Twitch. Yo. Trying to build my Twitch audience, and I appreciate it. I think you're the only one that's actually on Twitch right now watching with me. So let's go ahead and pull it up in Safari. If I pull up the stream, does that mean I'm watching myself as well? So it is. Let's go. That's so cool. That's so fun. I could do this. So I definitely appreciate y'all kind of watching this. What we're doing here, just to kind of summarize, this is day 3. And we're coding GPT-2. And as you can see, this is these people have been doing this for decades. Literally, this is their life's work. And Andre Kaparthi has been, generous enough to, he's a phenomenal teacher online to spread the knowledge. And then other people have been taking that and also sharing their knowledge of hey, we can do this for MLX, and then sharing that across. And so what we're doing is we're kind of sort of benefiting from this whole knowledge tree. So it's hey, why not, right? So I just thought this is a good time for us to kind of join together and share knowledge together and stuff like that. And there's a lot to take in. And for me, I could speed read everything, but then I would miss so many concepts. And I feel we're at such an important part of our learning journey that it's really important to really truly understand what these terminology means. This is my first time kind of playing around with this stuff. I've been playing around with OpenAI and ChatGPT and prompting and stuff, so I've kind of know how things work from the upper layer, going down this way, but I don't really know too much at the lowest level. My goal is to kind of start Infinity Mirror. Yeah. That's awesome. And so I also got the professional setup here. So we got this crispy cam here. So yeah, my goal is to like really get down to the fundamental layers and figure out how this stuff really works. And kind of just chunk this out so that it's easier for everyone to digest. It's just the way that I learn. So if you're trying to vibe with me, I really appreciate that you've been vibing. Definitely sign up for the email list at rayfernando.ai. So rayfernando.ai. Yeah. And yeah, rayfernando.ai. Okay. So when you go here, just pop in your email and then we'll stay connected because I want to connect with you and you're on the same wavelength and we're trying to improve our skills because this is the future. Like learning how to do this and learning to understand how this works. There's just so many opportunities and there's such a shortage of engineers that all of these companies need to just figure out, how to train a model. How does it work? How can we optimize something? Our team needs to do X, Y, Z and so forth. And like OpenAI is hiring, Anthropic, and there's just no shortage of companies that are continuing to grow. And they're using this architecture, but then it's just going to be super helpful for other programming languages in the future as well. So like there's a new programming language that Chris Latner is pioneering called Mojo, which is going to be building on top of this. There's, the infrastructure teams like Grok who are using their own stuff, but then are also using these types of things. And, just to understand a little bit of how this stuff is work, how the data works and how it trains, it's just a good way to kind of get started. So yeah, as you see, we're just going to keep going every day. I'm going to show up every day for you. That's right. Every single day we're going to show up. We're going to be here. And if you're not here, you can just rewatch my live stream. And I have a YouTube channel. You know what? I should put my YouTube channel in here because I don't have it. YouTube at Ray Fernando 1337. Let me put that I'm going to put that in the stream right now. So in here, in my live, I'm going to create a playlist called GPT from scratch. That way you'll be able to follow along. So in my live section, we're gonna you could just keep going through and just kind of rewatch them. And so that's how we're going to be doing this every day, showing up, taking off a chunk of this, and then moving forward. And if something doesn't make sense, just going to run it through a language model, going to run it through you. I have some friends I can give a call who are already like way ahead of me and just say, hey, I've been doing this so far. I'm kind of hitting a wall. I still don't really understand this. Like, what does this mean? And then boom, like they'll get the hookup. So that's what's going on. I really appreciate y'all just hanging out with me on this late night vibe as we're chilling. I got the music going. Yo, shout out to audio with the music and the beats. I love this. And this is the vibe that we do with you, with me, with you. All right. So if you haven't had a chance, check out Ray Fernando on X. So x.com at Ray Fernando 1337. Yo, okay, it's 8:30 in your time zone. Okay, what time zone are you in? It's 8:30. Sips morning coffee. Let's go. Are you in Japan? Actually, what time is it in? Hold on. Let him cook. Let's see. I have this clocks app. 8:30. Let's see. It is in Sydney. It's 3 p.m. UTC -3. Okay, bro. I don't know what that means. I could probably Google it right now, but I'm just trying to. Yeah. UTC -3. UTC. Oh no, UTC +3. Time zone. Papa military time. It's the Baltics. Yo, you're out there. Okay. Okay. Yeah. Oh my gosh. Baltics location. We're going to spy on you right now. The Baltic Sea. Okay. Yeah. Norway, Sweden, Finland. Oh, okay. Estonia. It's popping. Definitely appreciate y'all. Stealthy, not creepy at all. No. It's just a vibe. We're here to vibe. Definitely appreciate that. Yeah, give a thumbs up if you're vibing right now. And then also hit the retweets. Mad people will be doing on the retweets. So yeah, we got to get this number up. Can't just have one on the retweets. Yeah, because that way, so the whole point of like X for the retweets as well is the fact that like we want other people who are our friends, who are like nerdy like us, or who want to just kind of know some more information. It gets it out there to them. It's just a network effect, really. And that's how the algorithm works. So just by giving the likes, giving that thumbs up, giving the retweets, basically gets it out to more people. So no, definitely appreciate the stream. You know, even if you don't even like it, just retweet it. Drop a comment saying, yo, this guy, you know, is going too slow. But if you're on that vibe, if you're on the chill vibe, he's a cool guy. You should check him out. Like, that's all. You know what I'm saying? Like that's all we ask for. So that's what we're talking about. So yeah, on here, I have my YouTube channel. And actually, I'm going to do that right now. I'm going to drop my YouTube channel. So I can give you a sneak peek onto kind of how the Notion notebook works, which is really cool. But basically, I just go on Notion, and then it's going to update like my website real time. So Notion, Notion, where'd you go? Oh, my live streams are here. Okay. So GPT from scratch blog. I'm going to open that up and then drop my YouTube link in here. So it's my YouTube channel, and then live streams. Create as in bookmark streams embed. All right, cool. So I have it actually uploaded, which is right here. And in no time, if I just refresh my website, it should probably do it. Command Shift R. Oh yeah, since I'm running Next.js, I think I have a task that runs every couple of minutes or so, which will just pull the latest from the notebook. Oh, here it is. Yeah. And then refresh the page and do a server-side re-render. Let's go. Okay, here we are. So that's my YouTube streams. If you click this, basically we'll take you to the streams of where everything's kind of at. And these are all the live streams that I've done. You can even watch the one where we interviewed Chris Latner, Simon Willison, talked about Distiller 1. This is my favorite piece of technology here. We're just kind of going off the side. This is the chill side now. Now we're at the past 45-minute mark, but this is really cool. So I have a video about this coming up. Let's see. Yeah, Distiller 1. So this is an e-ink display, which is so baller. And like you can literally talk to it and it's going to draw like information on here. And it's a dev kit right now. So you can only play with this as a dev kit. You can take photos, you know, do some cool stuff and program with it. So actually, let me just hit you up. So since you've stayed on this long, I'm going to give you a little bonus tip here. So it's PAMIR.ai. I'm going to drop this in the comments if you can see this. You may or may not be able to see this, but let's see. So check this out. This is it like Rabbit R1? No, it's better. Because these guys are not scammers. I mean, not that they're scammers. Allegedly. No, this is way better than that. Like, it's an actual dev kit, and it's Raspberry Pi. So you can SSH into it, and the dev kit is, let's see, SDK. Oh, no, hold on. Whoops. Developer dot. Oh, man. Docs.PAMIR.ai. So they have an SDK, and in their SDK just shows you how to like get to the apps and stuff and set up the Wi-Fi, like exit the program and get things set up. And then this is for the getting started. The Distiller SDK is written in Python, so you can SSH in and like literally run your apps. It's just, they're all just running in Python. And it's basically got the, here we go. Yeah. So let me get you here. So if you scroll down, this is the device. I'm getting a little bit of preview of what's going on. So this is the board. So it's a handheld device that lets you deploy offline AI app or game. Make it your own. Take it anywhere. SoC. This is the board that's basically in there. So it's a user upgradable SoC. So you can change that out, which is fire. You have the quad core guy. You have 8 gigs of RAM, e-ink display, NFC, Bluetooth, 5 megapixel camera, audio in and out. And you have the M2 expansion, which is literally right here on the side that you may not be able to see right here. and then you can pop out and put an external GPU. So that's so crazy. So yeah, that like Rabbit R1, like get out of here with that. You know, it's like it doesn't even have. It's like way beyond that. So has a UI framework, and then these are some of the demo apps and stuff that I have on here. So PAMIR.ai, PAMIR.ai, and this is these guys, and then you should be able to pre-order it today. I think they're, let's see, buy now. Yeah, it's about a 1 month lead time to do the pre-order. So that's the first edition. If you get the Founders Edition, yeah, it's the same thing. PCB only. Yeah, everything is out about, I think, yeah, 1 month lead time. Yeah. So this is kind of what the stuff looks like with the board, with all that stuff. So yeah, that's kind of is what it is. So cool. These guys are awesome. And I have a video dropping on this guy soon. So stay tuned throughout the weekend. And basically, I'll give you my pitch right now. About it's not even a pitch. It's like I don't have any like financial relationship. I bought this stuff because I just love AI tech. But if you don't know by now, edge computing is kind of like the trend right now. Is a big reason why I'm trying to learn how to code GPT-2 from scratch. Is because learning how to control and make language models, this can run offline. So I could talk to it and do whatever, and it's going to do its own like diffusion thing and draw images. You know, it has its own like, you know, language model that runs on the device without an internet connection, and it generates stories and plays games. Like if I can figure out how to code and like make my own language model that can run on this guy, it's game over. Like this is like where it's going. You know, if you can get that on the like Casio size watch and stuff and do that, it's like even more game over. So that's the future. And then these guys are part of that whole movement. So they created their own board there. And so they take the chip that's running from the Raspberry Pi, put it up on there, and then you can even connect an external GPU if you wanted to. And now you have an edge computing device that doesn't connect to the internet, that is running a language model, and you're set. So that's the future of where I see some of this stuff going, and people are trying to do that. And so with Humane, the AI pin, that still requires an internet connection. And what's even worse is that it requires a constant connection to the cell network, which you pay for $30 a month or something like that. And it's like, bruh, I already have my phone. So like, and like, it's just okay. And I can, the thing about it is like the SDK right now is currently closed by them, and they're planning to open up for third parties, but you can't really go in and talk to a language model. They want you to do everything through their cloud, where this is on device. This is an actual edge device. It's running on the device there. So that's the whole thing. But isn't the main thing for LLMs is actual data as in a knowledge base? Or is the purpose to be more specialized LLMs? So I think that's what the discovery is happening right now. I'm seeing some innovations with Phi and like the smaller language models, like with Google and Gamma. And they're like 1.5 billion parameters or 1.9 billion parameters. And, you know, they're able to do specialized things. Same with Apple. Like they've got these smaller language models that are running. And so those are doing very, very specific tasks. So this can kind of be the same thing here, right? There's certain things that you want or need. You know, like if you want to generate a game or play something that's really interesting, this can connect to the internet if you connect it to Wi-Fi. So it's like, if you want to do something like look up some information, you know, you can do that, and it can actually try to process your requests, and it can maybe understand that like, hey, the request that you're asking requires, you know, multiple requests, or maybe reorganize your requests so that it can send it out to the internet in a like multiple query fashion. So that's kind of like, I'm thinking about Perplexity. So whenever you type in a question, it's like trying to better understand what you're asking. And so that's why these like maybe especially smaller like edge models can maybe do that, or have an interaction with you faster before, like while it's trying to get more responses from the internet, you know, you can have this back and forth, and it's just going to fill in those dots there. So that's kind of where I'm kind of thinking this could be heading. So that's kind of where we're at with that. So yeah. All right. Gotcha. Yeah. Cool. I'm glad it's kind of like making some sense there, because it's kind of a lot to take in, if you know what I mean. So yeah. So this is how we're doing it here today. So I'm going to show up tomorrow. I just got like this new camera setups thing. So that way you're having like this, you know, this camera right here with my cool fancy lights. And then you also get this other fancy drippy, like really good looking lens and stuff like that, and got the setup here. So appreciate y'all joining in. If you haven't had a chance to check out rayfernando.ai, definitely hit the retweet button on X for the stream. That definitely helps to get out there to more folks. So that way we can, infiltrate and spread the knowledge and share with the world what we know. All right, y'all. See you tomorrow.